Okay, we will continue the questions of the same topic. Now in our workbook, this is question number 6. This is question number 6. By considering the following block diagram, one block diagram which is given to you. Now this is the block diagram which is given to you, and he is giving, by considering the following block diagram which is related to a first order system, is having a gain of system gain is given in the question itself is 2, and system time constant is also given in the question, which is 0.4 seconds. Then determine the value of K1 and K2. Now first what we are doing is, now we will try to simplify this block diagram first. Now this is the closed loop control system with negative feedback, C of S by R of S, which is equal to G of S by 1 plus G of S into H of S. Therefore, which is equal to K1 by S divided by 1 plus K1 by S into H of S is K2. This is the closed loop control system transfer function, which is equal to K1 by S plus K1 K2. This is the first order system. This is the first order closed loop control system transfer function. From the block diagram, now this is the first order closed loop control system transfer function. This is the first order system. But what is the standard first order system with gain and time constant? The standard first order system with gain and time constant is C of S by R of S, which is equal to K by 1 plus tau S. You know that, right? Now therefore, K is system gain 2, 1 plus tau is 0.4 seconds into S. But this is in the time constant form. This is in the pole 0 form. S plus P means pole 0 form. But this is the time constant form. So you converted time constant to pole 0 or pole 0 to time constant when we are comparing the two transfer functions. If you want to compare the two transfer functions, the two transfer functions should be in the same form. And therefore, I want to convert this into time constant form. So K1, K2, if you take it as a common, 1 plus 1 by K1 K2 into S. Now this is K1. Then this K1 cancel. 1 by K2 by 1 plus 1 by K1 K2 into S, which is equal to 2 by 1 plus 0.4 into S. Now while comparing these two, K2 which is equal to 1 by 2, which is equal to 0.5, 1 by K1 K2 which is equal to 0.4, therefore K1 which is equal to 5. Now this is the given transfer function from the block diagram, and this is the transfer function with gain and time constant. If you want to compare the two transfer functions, the two transfer functions should be in the same form. You know that there are two types of the transfer function. One is time constant form, another one is pole 0 form. So you converted time to pole 0 or pole 0 to time, then only you can comparison. Comparison is possible. And this is the K1 and K2. Now this is question number 6. You just note down. Okay. Now we'll see question number 7. Now question number 7, which is a very simple question. The transfer function of a first order system is given as, the transfer function of a first order system is given as 10 by s plus 2. What should be the response for unit step input at t equal to 5 seconds? Which input? Unit step input. R of t equal to u of t equal to 1. Now what is R of s? R of s is 1 by s. Therefore, what is the response? Means I want output R of s into 10 by s plus 2. Therefore, C of s, which is equal to R of s, is 1 by s into 10 by s plus 2. So do the partial fraction, or you do the LCM directly. 5 by s minus 5 by s plus 2. So 5 into 2, 10, right? Therefore, apply inverse Laplace transformation. Apply inverse Laplace transformation. C of s is C of t, which is equal to 5 minus 5 into e power minus 2t. So what is C of t? Now this is C of t, which is equal to unit step response 5 into 1 minus e power minus 2t. 5 into 1 minus e power minus 2t. Now what he is asking? He is asking the response for unit step input at t equal to 5 seconds. He is asking where at t equal to 5 seconds. At t equal to 5 seconds. Therefore, C of t, which is equal to 5 into 1 minus e power minus 2, 5 into 2, 10, e power minus 10. This is the response at t equal to 5 seconds. Now your option says, this is option B. Okay, note down this. At t equal to 5 seconds means, therefore that is a time domain. Therefore I convert it into time domain. Okay, these are a few examples of that particular first order system and the problems of the first order system. Okay. Now you know that the total time domain analysis is nothing but which is both transient state analysis as well as the steady state analysis. Okay. Now this is the topic. Now I want to change that. Whatever we are doing is the time domain analysis of the first order system. Now we will see the time domain analysis of the second order system. Okay. Now the time domain analysis of second order system now we are going to be studied. Okay. Now this is the actual practical system. Most of the practical systems are the second order systems. Okay. So this is the very important for the GATE examination point of view. This topic is. So now we'll find the transfer function first. Now this is the block diagram which is given to you. Now this is the forward path gain. Now this is the forward path gain. Now the closed loop control system transfer function C of S by R of S, which is equal to G of S by 1 plus G of S into H of S. Now the closed loop control system transfer function, numerator is numerator. Numerator is numerator. Denominator is denominator plus numerator. Denominator of open loop transfer function plus numerator of open loop transfer function. This should be the closed loop control system transfer function. Therefore, which is equal to omega n square by s square plus 2 plus omega n square. Now see, this is the closed loop control system transfer function. The highest power in the denominator polynomial is 2. Therefore, this is nothing but a standard second order system. This is the standard second order system. This is the standard second order system transfer function. This is the standard second order system transfer function where this omega n is undamped frequency of oscillations or undamped natural frequency of oscillations. Undamped natural frequency of oscillations. Units are radians per second. Undamped natural frequency of oscillations, units are radians per second, where zeta is, this is zeta, okay, not eta, zeta. This zeta is nothing but damping factor. This zeta is nothing but the damping factor. Now this is the highest power in the denominator polynomial. Our highest power in the characteristic equation is nothing but 2. This is the standard second order system. Okay, and this is the standard second order system where zeta is the damping factor, where omega n is undamped natural frequency of oscillations. Okay, now this kind of a standard second order system, previously first order system, now we are taking and we'll do the transient state analysis and steady state analysis. In the same manner here, first we want to do the second order system. Now we'll take the transient state analysis as well as the steady state analysis. Okay, this is the standard second order system and we'll take the transient state analysis. The transient state analysis is nothing but the response of the control system after applying some input. Apply the input, see the response. That is nothing but the transient state analysis. Okay, it may be impulse input, ramp input, parabolic input, whatever it may be. Okay, first you take the standard system and next we will see the transient state analysis and after that steady state analysis also. Okay, now students, you just see here. Now this is the standard second order system where omega n is a frequency of oscillation, where zeta is a damping factor. Now this is the first time, students, then we just see the second order system. Now that's why first we will see the theoretical analysis. Okay, what is the theoretical analysis? The theoretical analysis is the analysis after applying the impulse input. So this is the time domain analysis of the second order system. Now under that, then we will see the impulse response. Okay, now we will see the impulse response of this second order system. The impulse response of the second order system. Now when you can get the impulse response? The impulse response is the response after applying the impulse input. Therefore now first you want to apply the impulse input. C of S, which is equal to R of S into omega n square by S square plus 2 zeta omega n into S plus omega n square, which is nothing but C of S. Now the R of S. Now what is R of S? R of T is nothing but the impulse input. R of S is nothing but 1. Am I right? Not? Therefore, now see here, R of T is the impulse input delta of T. Therefore, R of S, which is nothing but Laplace transformation of delta of T, which is equal to 1. So C of S, which is equal to R of S, is 1 into omega n square by S square plus 2 zeta omega n into S plus omega n square. Now R of S is 1. Whenever R of S is 1, impulse input. This is the impulse input. When the impulse input is given, then this response is nothing but the impulse response. This is the impulse response. Now the students, this is the impulse response when we are giving the impulse input. This is the impulse response when we are giving the impulse input. So we have one important point here. When I am asking a question like this, S plus 1 by S plus 2, when I am asking a question, where is 0? 0 is at minus 1. Where is pole? Pole is at minus 2. When I am asking a question like this, S plus 2 by S minus 3 into S plus 4. Now where is 0? You are saying 0 is at minus 2. Where is pole? Sir, 0 is on plus 3, positive real axis. Pole is at positive real axis. One more pole is on negative real axis. Like that you can easily say the answer, because here poles and zeros are available directly. Am I right? Not? Then if you see here, the second order system behavior, the second order system complete behavior is depends upon the damping factor zeta. The second order system complete behavior depending upon the damping factor zeta. Until unless if you don't know the damping factor zeta, you cannot able to find the system transfer function or system behavior or system analysis. You cannot say anything, you cannot say time constant, you cannot say any parameters if you don't know the damping factor zeta. That is the reason why the second order system behavior is completely depends upon the damping factor zeta. So now we are at the theoretical analysis, because this is the impulse response. Now in the theoretical analysis itself, you can find what should be the damping factor zeta and what is the suitable damping factor zeta, such that it is useful to design a best second order system. One important question is not only the time domain analysis, but also now you have to find what should be the suitable damping factor zeta, such that we can get the good response of the second order system. Now keep that particular point in your mind and we'll start the analysis. Now we'll start with the case 1. This is in frequency domain, I want in time domain. Therefore, now this is case 1. Now what is case 1? Now case 1, which is nothing but when damping factor zeta equal to 0. Now this is case 1 when damping factor, this is case 1 when damping factor zeta equal to 0. When damping factor zeta equal to 0, what happened? Now when damping factor zeta equal to 0, what is impulse response? Now C of S, which is equal to omega n square by S square plus delta equal to 0. This is omega n square. Don't do the partial fractions, don't do all such kind of things. You have a direct location. Now the pole is available directly. Once the pole's location is available, you tell me all the answers. Okay, every parameter you can say. Now S square plus omega n square equal to 0. Now where is the pole location? Now the pole location is S equal to plus or minus j omega n. Now this is the two poles P1, P2. Now these are the two poles 0 plus or minus j omega n. Now these are the poles location. Where is the pole location? Poles lies on imaginary axis. One pole is at plus j omega n and another pole is at minus j omega n. Now the poles which lies on imaginary axis, the poles which lies on imaginary axis which are not repeated, then you can easily find all the parameters. Okay, first you tell me the poles which lies on imaginary axis which are not repeated, therefore system is marginally stable. Time constant, negative of reciprocal of real part, no real part. This is the real part and this is the imaginary part. No real part, therefore minus 1 by 0, time constant is infinity. Imaginary part, therefore the frequency of oscillations is the frequency of oscillations. Imaginary part will give the frequency of oscillations which is equal to omega n radians per second. This is the frequency of oscillations present in the response which is omega n radians per second. Now what is the impulse response in time domain? The impulse response in time domain C of t, which is equal to some constant into e power real part. Is there any real part? No, e power real part is 0. Sine or cos, whatever it may be, sine or cos. Imaginary part, what is imaginary part? Omega n into t. Recollect what is the impulse response and a shortcut method. K into e power real part into t. Sine wave or a cos wave, not a problem. Sine or cos into imaginary part into t. See, go to the basic classes. This is the impulse response. K into e power real part, sine or cos, and imaginary part into t. Now this is the impulse response. Now peak amplitude is plus k. Peak amplitude is plus k. Let us assume plus k. Minimum amplitude is minus k. Peak amplitude is plus k. Minimum amplitude is minus k. Peak to peak amplitude is 2k. And the frequency of oscillations omega n radians per second. And the frequency of oscillation is omega n radians per second. Now see here, now peak amplitude is constant amplitude and frequency of oscillations from minus infinity to plus infinity irrespective of the input. That particular system response is called as a marginally stable system. Any control system response maintained constant amplitude and frequency of oscillations irrespective of input, and that system is said to be marginally stable. Now one more thing, here how the response, you just see the impulse response. This is the impulse response. The impulse response is maintained constant amplitude. Am I not? Here amplitudes are decreasing? No. Amplitudes are increasing? No. The amplitudes are maintained. Constant amplitude. Now in the previous basic classes I am giving one word. When amplitudes are decreasing, when amplitudes are decreases, now that we call as damping. But when amplitudes are increases and amplitudes are decreases, damping. When amplitudes are increases, the system signal amplitude should be increases. But here the amplitude is constant. The constant amplitude means there is no change in amplitude. Am I not? Now there is no change in amplitude. Therefore, this response is called as un means no change, undamped response. Therefore, when damping factor delta equal to 0, then I put one name here. This is nothing but undamped system. Don't say system, undamped response. Now this is the undamped response when damping factor delta equals 0. But in books you see undamped system. Yes, undamped system is nothing but that system produces undamped response. Undamped response is the response where the response is having constant amplitude and frequency of oscillations. Constant amplitude, no change in amplitude, undamped response. Okay. Now, the damping factor delta equals 0 is nothing but the undamped response. Can you prefer practically a damping factor delta equal to 0? No, we never prefer practically a damping factor delta equals 0. If damping factor delta equals 0, system is marginally stable. Okay. Now, this is case 1, damping factor delta equals 0. You will see the remaining cases. Then first you note down this. Okay, students. Now this is the impulse response of the second order system when damping factor delta equal to 0. Okay. Now this is the second order system when damping factor delta equal to 0. Now this is not preferred practically because system is marginally stable. Okay. We always prefer a stable system. Okay. Don't write marginally stable system is not preferred. We will see again in the, this is impulse response, theoretical response. Again we will put a practical response. There we can eliminate all these delta values. Okay. Now this is the, therefore when damping factor delta equals 0, this is called as undamped response because the name we can put based on its response. The response is maintained constant amplitude and frequency of oscillations. Understand? Now the response is maintained constant amplitude and frequency of oscillations. Now therefore this response is called as a undamped response. Now this is the undamped response. Therefore the frequency of oscillations in this response is called as, this is undamped response. Therefore the frequency of oscillations in this response is called as an undamped response or not. Therefore this is undamped response. The frequency of oscillation in this response is called as undamped frequency of oscillation. That's why omega n we will put already a name for that, undamped natural frequency of oscillations. Okay, this is undamped natural frequency of oscillations. See, when damping factor delta equals 0, the response is consisting full of oscillation. It is completely oscillatory in nature. Completely oscillatory in nature. Completely oscillatory in nature. Okay, this is full of oscillations. It is completely oscillatory behavior when damping factor delta equal to 0. Okay, then we will take another case. Now case 2. What happened? What should be the changes when damping factor delta equal change? When damping factor delta changes, location changes. Location changes, system behavior is also changes. Now we'll see case 2. Case 2, which is nothing but when damping factor zeta, which is equal to 1. When damping factor zeta, which is equal to 1. S square plus 2 zeta is 1 into omega ns plus omega n square. This is omega n square. Now therefore C of S, which is equal to omega n square, a square plus b square plus 2ab, S plus omega n whole square, a square plus b square plus 2ab, S plus omega n whole square. Now see here, now the poles location is available directly. What is the poles location? Now these are the two poles, which is minus omega n comma minus omega n, repeated poles on the negative real axis. Now this is the real part, minus omega n, but poles which are repeated. But we know that whenever the poles lies on the left hand side of S plane, then obviously without any second thought, system is stable. Time constant is negative of reciprocal of real part. Therefore 1 by omega n seconds. No imaginary part, only real part. Therefore oscillations frequency is 0 radians per second. Only one simple logic, if you remember or not, I don't know. Whenever there is imaginary part, sine or cos term, no imaginary part, no sine or cos term, only exponential term. Only simple logic. Okay. Now this is the frequency of oscillation. Then what is the response in time domain? Now the impulse response in time domain is, k into e power real part. What is the real part? Real part is minus omega n into t. Sine or cos, is there any imaginary part? No imaginary part, nothing. Therefore frequency of oscillation is 0. Poles are repeated. If the poles are repeated, then this is nothing but t. If the poles are repeated, Now the poles are repeated means one extra term is nothing but t. Now you know how to draw the response of exponentially decaying and linearly varying signal. One is ramp, linearly varying. Another one is exponentially decaying. This is linearly varying and this is exponential decay. Multiplication is nothing but a common area, common limit, common boundaries. Now you just compare with the previous case. When damping factor delta equals 0, the behavior is completely oscillatory in nature. Am I not? Delta equal to 0, the response is completely oscillatory in nature. The response is completely oscillatory in nature. But now when damping factor delta equal to 1, then is there any oscillations? What is the frequency of oscillation? The frequency of oscillation is 0. If strictly speaking, no oscillations, nothing. Am I not? So I just saying this is one critical point. Why this is called as a critical point? When damping factor delta equals 0, it is completely oscillatory in nature. But damping factor delta 0 to damping factor delta 1, all the complete oscillator nature is gone and it just produces a small positive half cycle. Am I not? At this critical point, produces a small positive oscillations, positive half cycle, don't say oscillations, positive half cycle. At this critical point it will not stop, it will continue, assume it will continue. So one more negative half cycle, one more full cycle, there may be a chance of time period, there may be a chance of frequency, and whose nature is same as that of delta equal 0's nature, it is completely oscillatory nature. But here at this critical point, all the oscillations are wind up, oscillation nature is gone, and frequency of oscillation is 0 radians per second, produces a small positive half cycle. Therefore that's why this point is called a critical point. And what is the amplitudes? All the amplitudes, as time increases, amplitudes are increasing or decreasing? Sir, in the starting the amplitudes are increasing. I am not asking about the starting, I am waiting for t tends to infinity. When t tends to infinity, the amplitudes are decreasing, therefore this is called as damping. Decreases the amplitude is called as damping. Decreasing the amplitude is called as damping. This is damping, this is critical point. Therefore when damping factor delta equal to 1, this is called as critically damped response. This is called as critically damped response. Critically, amplitudes are decreasing, therefore this is called as damping, critically damped response. Critical point, because at this critical point all the oscillation nature is gone, that's why this is critical point. Amplitudes are decreasing, therefore this is called as damping, critically damped response. Okay, can you prefer practically critically damped response? Yes, obviously, because system is stable. Okay, now you just note down this. Okay, now this is case 2. So we can consider damping factor delta equal to 1 because system is stable. Okay, but we don't consider damping factor delta equal to zeta equal to 0 because system is marginally stable. Whenever the amplitudes are decreasing, use the word damping. Clear? Now this is the characteristic equation. First you find the roots of this characteristic equation. S square plus 2 zeta omega n into s plus omega n square equal to 0, which is equal to P1 P2 minus B plus or minus square root of B square, square root of B square 4 zeta square omega n square minus B plus or minus square root of B square minus 4AC by 2A. Now which is equal to minus 2 zeta omega n plus or minus under root of 4 if you take it as 2 as common, under root of omega n square if you take it as a omega n as common, zeta square minus 1 by 2. Therefore, now these are the poles location, students. These are the poles location. Now which is nothing but minus zeta omega n plus or minus omega n into square root of zeta square minus 1. These are the poles location. Am I not? These are the poles location. Now this under root is positive. Zeta square minus 1 is greater than 0. This zeta square is greater than 1. Then this zeta is plus or minus 1, but we consider only positive side. Okay. Now this is the poles location when damping factor zeta is greater than 1. These are the poles location when damping factor zeta is greater than 1. Now this should be treated as case 3. Okay. Now this is damping factor zeta which is greater than 1. We can consider as a case 3. But now you see, don't say this is real part, don't say this is imaginary part. Real part, imaginary part is separated with J term. Okay. This is totally a real part. This is completely a real part. Now this is assume minus 2 and this is minus 2 plus 3 or minus 2 minus 3 like that. Okay. So totally this is a real part. So when damping factor zeta greater than 1, poles are lies on negative real axis but which are not repeated. This is one pole is minus zeta omega n plus omega n into square, another pole is minus zeta omega n into minus. Okay. Now we will see case 3 as a damping factor zeta is greater than 1. We will see this one. Okay. Before that you just take the roots of this.